Hello my schoolers, you are welcome to my school YouTube channel and my name is Frank. In today's video we shall be learning about current electricity. So relax, do not go anywhere, and we'll be right back. You are welcome back to my school YouTube channel. Like I said earlier, in today's video we shall be learning about current electricity. So before we begin with our lesson, let's quickly run through the objective of today's video lesson. Objective number 1, explain electric current. 2, understand the meaning of resistance as opposition to the flow of charges. 3, identify all the component parts of a simple cell and an accumulator. 4, solve problems involving series and parallel connections of resistors and cells. Then 5, state the factors on which the resistance of a uniform wire depends. So let's begin with our lesson. So while static electricity deals with electric charges at rest, current electricity deals with electric charges in motion. Okay, so we define current electricity, or we say current electricity involves the movement of electric charges. Okay, so when a cell or battery connected to a metallic wire, it creates a current as free electrons move through the wire. The potential difference between the battery terminals drive this movement. Continuous current requires a constant source of moving charges provided by primary and secondary cells. So let's talk about primary and secondary cells. So let's begin with primary cells. So primary cells generate current through irreversible chemical changes and cannot be recharged. So these primary cells, they have high internal resistance and can only supply a limited current for a short duration. So examples of primary cells are the simple cell, the Daniell cell, and the Leclerc cell. Okay, so each of these cells, we are going to be explaining them one after the other with also their diagram. So let's begin with the Daniell cell. Okay, so the Daniell cell consists of a copper vessel filled with saturated copper sulfate solution, a porous pot containing dilute tetrasulfate 6 acid, okay, also known as sulfuric acid, which is H2SO4, and amalgamated zinc rod immersed in the acid. Let's move to the next slide. So this is the diagram of the Daniell cells, okay, and these are the different components that made up the Daniell cell. Okay, so this is the porous pots. Okay, and the porous pot contains a zinc rod. Then inside is the dilute sulfuric acid. Then the outer vessel is the copper vessel. Then inside the copper vessel we also have a copper sulfate solution inside. Okay, so let's talk about the another type of primary cell, which is the Leclerc cell. So the Leclerc cell is of two types, the wet type and the dry type. So let's begin with the wet Leclerc cell. So this is the diagram of the wet Leclerc cell. Okay, so it has an outer glass jar. Inside the glass jar is ammonium chloride. Then inside also you also have a porous pot, and inside the porous pot you have magnesium dioxide and powdered carbon, and also with a carbon rod, okay, which serves as the positive terminal of the cell. Then inside the glass jar you also have a zinc rod which serves as the negative terminal of the cell. So let's move to the next slide to properly explain it. Okay, so the dry Leclerc cell consists of a carbon rod in a porous pot filled with magnesium dioxide and powdered carbon, surrounded by a glass jar containing ammonium chloride and a zinc rod. So the carbon rod acts as the positive terminal while the zinc rod serves as the negative terminal. Then the ammonium chloride is the electrolyte and manganese dioxide functions as the depolarizer. The disadvantages of the Leclerc cell include a slower depolarization rate compared to hydrogen liberation and difficulty in portability due to potential spills. Okay, so now let's talk about the dry Leclerc cell. So the dry Leclerc cell is the common radio or torchlight battery. Okay, it comprises of a carbon rod in a muslin bag filled with manganese dioxide and powdered carbon, surrounded by a zinc container containing a paste of ammonium chloride. The carbon rod serves as the positive terminal, while the zinc container serves as the negative terminal. Ammonium chloride functions as the electrolyte, and the mixture of manganese and powdered carbon serves as the depolarizer. At the bottom is a cardboard disc to prevent the carbon rod from touching the negative zinc container. At the top is a pitch seal and a brass cap. Let's move to the next slide so that we can see the diagram of the dry lakelage cell. Okay, so over the carbon rod, like the wet lakelage cell, the rate of depolarizer is slower than that of hydrogen liberation, and so it cannot maintain current for a very long time. So this is the diagram of the dry lakelage cell. Okay, so this is the carbon brass, while this is the pitch seal. Then the body here is an insulating cover, while here we have the carbon rod, which serves as the positive terminal. Then inside is a mixture, inside the muslin bag, okay, is a mixture of manganese dioxide and powdered carbon, while inside the insulating cover, okay, is a paste of magnesium chloride, and that actually serves as the electrolyte. Okay, then here we also have a muslin bag. Okay, then we also have a cardboard disc. So this cardboard disc prevents the carbon rod, okay, from touching the base of the container. That is the base of the muslin bag. Okay, now let's move on to talk about the simple cell. So the simple cell is also known as voltaic cell, okay, but it is different from electrolytic cell. So the simple cell consists of a copper rod, which is the positive terminal and is also known as, or also called the anode, and a zinc plate, which is the negative terminal, also called the cathode, immersed in a container filled with dilute tetraoxosulfate 6 acid, or commonly known as sulfuric acid. So when the terminals of the copper rod and zinc plates are connected to a bulb using a conductor such as a metallic wire, the bulb lights up, showing that current is flowing through it. So let's move to the next slide so that we can see the diagram of the simple cell. So this is the diagram of the simple cell. This is the negative terminal, which is a zinc plate, and this is the positive terminal, which is the copper rod. Okay, while the electrolyte here is the dilute H2SO4. So whenever current is flowing, then this bulb lights. Okay, so basically when current is not flowing, then these bulbs will not be on, or it will not light. So this simple cell also has some defects, okay, which actually affects the amount of current it supplies and the time it supplies it. Okay, so the simple cell has two defects, namely polarization and local action. So these defects make the cell to supply current only for a short time. So what is polarization? So polarization occurs when hydrogen bubbles form around the copper plate, as you can see in the diagram of the simple cell above. These are hydrogen bubbles around the copper plate or the copper rod, creating a back EMF that opposes the current, the cell's EMF. This effect can be reduced or prevented by adding depolarizer like manganese dioxide or potassium dichromate. Then let's talk about the second type or second form of defect of the simple cell, which is the local action. So local action is due to impurities on the zinc plate. This situation leads to the dissolution. Let's move to the next slide. This situation leads to the dissolution of the zinc plate. Local action can be prevented by rubbing of mercury over the surface of the zinc plate, and this process is known or is called amalgamation. Okay, so let's talk about the secondary cell. So the secondary cell is also called accumulators. So secondary cells are those cells from which current is produced due to reversible chemical changes within the cell. The chemical reactions can be reversed when current opposite to the one it supplies is passed through it. A secondary cell can be recharged or restored. Okay, so once the charge inside is depleted, it can be recharged again. Okay, so the main advantage of secondary cells or accumulators over primary cell is that they have a very low internal resistance, and so they can provide large current for a long time with very little change in their terminal potential difference. They are used in motor vehicles to start the engines. Okay, so they are actually the batteries that is found in motor vehicles. Okay, so they are used to provide the spark required to ignite air, fuel mixture in petrol engines, and they also used to provide current in telephone cables. Okay, so these are some of the uses of the secondary cells. Let's move to the next slide. So there are two types of secondary cells, okay, namely the lead acid accumulator and the alkaline or nickel ion accumulator, also known as knife. So let's explain each of these type of secondary cell one after the other. So let's begin with the lead acid accumulator. The simple form of these cells consists of a positive pole of lead dioxide. So in some textbook, they may use the word lead peroxide. So they are still the same, or lead oxide cell, which is PbO2. Okay, so it does depend on the author. While a negative pole of lead plate and an electrolyte of dilute tetrasulfate 6 acid, which is H2SO4, or commonly known as sulfuric acid, is used as the electrolyte. So below is the diagram of the lead acid accumulator. So the negative terminal of the lead acid accumulator is the lead plate. Okay, that is pure lead, while the positive terminal is the lead dioxide or a pole of lead peroxide, while the electrolyte is dilute sulfuric acid. So let's move to the next slide. Now let's talk about the alkaline or nickel ion, also known as the NEF accumulator. So this particular type of accumulator consists of the positive pole of nickel plate, a negative pole of iron plate, and an electrolyte of potassium hydroxide solution, which is KO3. Okay, so below is the diagram of the alkaline or nickel ion accumulator. Okay, so the positive terminal is nickel plate, while the negative terminal is a pole of iron plate, and the electrolyte here for the alkaline accumulator is the potassium hydroxide. So now let's talk about using or discharging an accumulator. Okay, so when the accumulator is in use or being discharged, it means it is supplying current to an external load such as an electric bulb. So in this case, current flows from the positive terminal to the negative terminal, okay, when the key is closed. Let's move to the next slide. So this is the diagram of the accumulator when it is in use. So once the key, this place is closed, then current flows from the positive terminal. Okay, so after some time the bulb goes dim and off, and the ammeter will indicate no reading. At this stage, the accumulator is said to be discharged. Okay, so when the accumulator is fully discharged, the relative density of the acid falls to 1.15. Okay, now let's talk about charging or discharging an accumulator. Okay, so when an accumulator is discharged or is depleted, it can be recharged. Okay, so now I want to describe how you can recharge it or how you can charge the accumulator. When charging an accumulator, a direct current is passed through it in a direction opposite to that with which it supplies current. Let's move to the next slide. The positive terminal of the DC source, of the direct current source, is connected to the positive terminal of the accumulator, and its negative terminal to the negative terminal of the accumulator. So the diagram here shows how the accumulator is charged. Okay, so when the key is closed, the current flows, okay, from the DC source. The current from the DC source flows into the cell at the positive terminal and flows out at the negative terminal. The variable resistor, which is this arrow, is used to regulate the amount of current which enters the cell. Let's move to the next slide. Now, since the electrolyte is of very low resistance while the current is being monitored using the ammeter A, this is to ensure that only the current recommended by the manufacturer is used. When fully charged, the lead acid accumulator gives an EMF of 2.2 volts, and the relative density of the acid attains the recommended value of 1.25. Okay, so that is that about the accumulator. Now let's talk about electric current. So basically we are just going to define electric current, talk about the formulas for solving problems under electric current and the rest. So electric current is the time rate of flow of electric charge along a conductor such as a wire. Okay, so mathematically electric current represented with letter I is equals to quantity of charge, which is represented with letter Q, all over time, which is represented with letter T. So Q, which represents quantity of charge, is in coulomb, and coulomb is represented with letter C, while T is in seconds, okay, and it's represented with letter S. That is, seconds is represented with letter S, and I is in amperes, okay, which is represented with letter A. However, there are smaller units of current such as milliampere and we have microampere. So milliampere, 1 ampere is equals to 10 raised to the power minus 3 milliampere, and 1 ampere is also equals to 10 raised to the power 6 microampere. Okay, so the instrument used for measuring current is called ammeter, right? But if you want to measure smaller current, then you can use the milliammeter. Then very small current, you can actually detect all those ones using galvanometer. Okay, so let's move over to the next slide. So here we are going to be discussing about electric circuit. Okay, so an electric circuit is the part provided for the flow of electric current. So an electric circuit consists of cell or battery, which is the source of energy, then a conductor, e.g. a wire, through which the cell or battery is connected to a load. The load can be an electric bulb or a resistor. So there is a key. The key actually serves as a switch, or another word for key is switch, which serves to close or open the circuit. Now there are 3 types of electric circuit, namely the closed circuit, the open circuit, and the short circuit. So each of these circuits, we are going to be explaining them one after the other, okay, with also diagram to show them. So let's begin with closed circuit. So a closed circuit is the one in which there is no gap along the conducting part. Okay, as you can see in the diagram below, the key is closed and current flows through the conductor to the external load. So here is the key. So this is the conducting part. Okay, so there's no gap between the conducting part. Of course, here represents the cell or the source of the current or the source of the energy, while this is the conductor. Okay, so here the part is closed. So once the key is closed, then current flows, okay, from the cells down to the external load, which can be bulb or a resistor. So let's move to the next slide. Then we also have the open circuit. So for the open circuit, okay, there is a gap along the conducting part, meaning the key is open, and in that case current does not flow to the external load, as you can see in the diagram below. So this diagram you are seeing here represents the open circuit. So for the open circuit, no current flow because there is a gap in the conducting part. That is, the key is open. So in that case, no current will flow from the source of the current, which is cell, to the external load, which in this case could be a bulb or a resistor. Then we also have a short circuit. So a short circuit is a closed circuit which has no load on it, as you can see in the diagram. So this is a short circuit, even though the circuit is closed, okay, but it does not have any load on it. So in that case, we call this type of circuit a closed circuit. So let's move to the next slide. So on this next slide here, we are going to be talking about the simple continuity test. So the simple continuity test is just a kind of test that is used to test circuits. Of course, the simple continuity test can as well be used to test the components of a circuit, which we'll be discussing in the slides to come. Okay, so the simple continuity tester is a device used to detect faults in a circuit. So when a circuit is not continuous, that is broken circuit, then there is a fault in the circuit. A continuous tester is used to test whether a circuit is continuous or broken at a certain point. So when we say continuous, basically we are saying that there is flow of current, okay? But when we say broken, we are saying that there is no flow of current. So in that case, we can even say the circuit is open, Okay, so that is what we mean by broken circuit. Okay, so broken at a certain point. The tester consists of a bulb which lights up when there is continuous flow and fails to light up when the circuit is broken. So this is just an homemade simple continuous tester. So it consists of a battery, a resistor, a buzzer. So a buzzer is just like an alarm, okay? Then we have a probe, like a tester that you connect to the component. Once you connect these two probes to the circuit, then you will hear a sound. So the buzzer here will produce a sound, telling you that there is flow of current or that the circuit is continuous. But if you don't hear a sound, then it shows that the circuit is broken. Okay, so sometimes instead of a buzzer, you can also have a bulb, okay, which lights up when the circuit is continuous or which does not light when the circuit is broken. So this is where we bring the preview of today's video to an end. I believe you enjoyed it. You can watch the complete video by simply clicking on the link in the description below, and that will take you to my school website. There you will have to subscribe to enjoy the complete video. So in the complete video, you will learn about the symbols of components used in circuit. You will learn about EMF, PDF, you learn about the Ohm's law and many more. Then we'll also cap it up with some worked example. Okay, so I believe you enjoyed the preview of the video you just watched. If yes, please do not forget to hit the like button, click on the subscribe button, and lastly tap on the notification bell to get informed as soon as we release the next videos.